almost towards the end of this course. Most of the things have already been discussed in the class. So in this live session, what we'll do is it is an opportunity to have an interaction with you, one-to-one interaction with you. You have already posted some questions on the forum, and many of you wrote to me personally asking your confusion and doubt. I tried to respond to your email, and also our TA is continuously responding to all the doubts and confusions that you may have in the forum. So in this session, what will and the Google Sheet is also circulated to all of you, so that you can have you can post your question, and we can discuss those questions in this session. So what I will do is I have just picked a few questions from the forum and the few questions that I have received to my personal email. Not just not just this year. What I have been receiving from last couple of years. I have picked up some questions from that, some confusion from that, which I'll try to discuss in this session. While choosing the questions, I try to concentrate only on those, try to pick up only those which have been asked many times and which are the common confusion and mistake we do in structural analysis 1. And then as the session goes, you can post your question in the chat box, and if time permits, I'll try to address those questions as well. Okay, so let me share my screen so that I can yes, I believe you can see the screen on my computer. Yeah, there may be a time lag between for a few seconds time lag. So when you listen and see the screen, you please yourself try to synchronize it and put that entire discussion in a proper context. Okay, one question or rather one confusion or one doubt I have received many times from the students related to degrees of freedom, and then this another question related to degrees of freedom is when we draw the free body diagram of a support for a particular support, then what are the direction of the forces, what are the forces to be shown related to that. You see, degrees of freedom is, as the name suggests, it is a freedom of an object to move, right, in a three-dimensional space. Now, but then this is a philosophical definition of degrees of freedom, but that it has to be quantified. Okay, so for the quantification, the degrees of freedom is a number of independent information or the coordinates which we need to characterize the movement of a body, right? So degrees of freedom is a freedom of an object to move in three-dimensional space, and how it is calculated, it is determined. It is a number of independent. This independent term is very important. Number of independent information or the coordinates required to characterize the movement of the body. Now, if I have to tell you that, for instance, suppose take an example of this. Take a small square, right? And suppose this is undeformed. This is the configuration 1, undeformed configuration. You can say, or configuration on this is XY plane, I am giving an example in 2D. So suppose this object is somewhere here, and then this object moves to a place, moves to somewhere, and then object, this is the new configuration position of the object, right? Now, in order to characterize, in order to identify, locate the new configuration, what we need is, we need that what is this, so this object will first move in x direction, this object will move first in x direction, then object will first then move from the x direction, it will move to y direction, and then in the third case, in this position it will rotate, right? So you will get the final configuration this. So we need this information, we need this information, and we need this information. These all three informations are independent. By just from this information we cannot comment on these two information. Not if we only with this information we cannot comment on other two information. So these informations are independent, these motions are independent. So we need three independent movement to characterize the motion of this body, right? The movement of the body, or the deformation. In this case, motion may not be the correct word in the context of present course. The deformation of this body. So therefore, in this case, the degrees of freedom is 3. So in two-dimensional plane, any system you take, any object, any rigid object you take, any rigid object you take, it has a 3 degrees of freedom, 2 translation and 1 rotation. Similarly, if you take a three-dimensional object, in three-dimensional object you have 6 degrees of 6 degrees of 6 degrees of freedom. Okay. Now, now related to that, and the question is, suppose if we have a support, suppose you have a roller hinge support, okay, and then what is the now why do we provide support? Supports are provided to constrain some degrees of freedom. Okay, depending on which degrees of freedom you constrain, you have to represent the free body diagram accordingly. You have different number of different kinds of support depending on the different constraints against different degrees of freedom. For instance, if you talk about hinge support is, I'm again talking about two-dimensional plane. For a hinge support, this direction movement is restricted, this direction movement is restricted. Only movement allowed is the rotation. So this object can rotate like this. This object can rotate like this. So it has just 1 degrees of freedom. Now, when we draw the free body diagram, so if we have to draw the free body diagram of the support, the free body diagram will be, since the displacement is restricted in this direction and restricted in this direction, there will be a reaction to this at this support. So there will be reaction vertical reaction, there will be reaction horizontal reaction, but since the rotation is allowed at this support, there will be no the moment at the hinge support. Similarly, if you have a roller support, then at the roller support, you have 1 degrees of freedom is allowed, which is rolling on the plane, but then it can rotate and it cannot, 2 degrees of freedom are allowed. It can translate in this direction, it can rotate. Only restriction you have is, in this case, is the vertical motion. So if you draw the free body diagram of roller support, it will be like this, free body diagram roller support. Now, suppose you have a roller, something like this. You have a roller, you have a structure, then you have a beam, and then there is a roller here, and it is a plane. Now look at these rollers, this can roll on this plane, right? Now, in that case, when you draw the free body diagram of this support, the roller support, the forces you have to apply like this. The free body diagram of this will be, it can move in this direction, so it has a degrees of, it is free in this direction. Only restriction is the motion in this direction, so there will be a reaction normal to the plane. So this will be the degrees of freedom. So if you have a plane, you draw the degrees of freedom this. If this is hinge, then this will be the force from the roller, and this is the corresponding forces from the hinge. So this is how you have to show the forces or free body diagram of the support. So when you look at the support, I say it is roller, but then in which direction the motion is restricted, which direction the motion is allowed, movement is allowed. Depending on that, you have to show the free body diagram. Okay. Uh, uh, One question is asked is why do we have factor half in strain energy expression? Okay, if you draw the uh, so what I'll do is I have some questions which anyway I'll be discussing, and then parallelly the questions, whatever question I see in the chat box, I'll try to address them as well. So if you draw the strain for a linear elastic material, if it is a strain, if it is stress, then the relation between stress and strain will be this. This is the relation between stress and strain, and then the energy density you will get is the area of this will get the energy density. Okay, so this will get half into sigma into epsilon. So this is your energy density. Now this energy density will be multiplied with the volume to get the total energy. That's why this half sign comes here. Okay. Okay, so let us move on to the another confusion, that is sign convention. You see, when we talk, say for instance, what are the sign convention we have taken so far in bending and shear? If we have a bend, if we take a section of a beam like this, then this bending moment and this bending moments are considered as positive bending moments or sagging bending moment, right? And this bending moment, this is positive bending moment, and if the bending moment is this is negative bending moment, this is hogging bending moment. And if we try to visualize this, then this sagging bending moment will cause this kind of deformation in the beam, sagging in the beam, that's why it is called sagging, and this bending moment will cause this kind of deformation in the beam, which is hogging, that's why it is called hogging bending moment. So when you draw a bending moment diagram, that diagram needs to be drawn depending on whether the bending moment is sagging or hogging. So by default, when we say bending moment is positive or negative, it means whether the bending moment is sagging bending moment or hogging bending moment. But then when we use this bending moment in an algebraic equation, suppose when we two bending moments, we are adding or subtracting bending moments, then that addition or subtraction, that operation, algebraic operation, need to perform based on whether the moments are in same direction or opposite direction. For instance, in this case, both bending moments here and here, they are positive bending moment because they are sagging bending moment. But then suppose this is M and this is M1 and this is M2. This is M1 and M2. But when we do algebraic manipulation, when we write this in an equilibrium equation, then it will be M1 minus M2 if you assume that clockwise moment is positive and anti-clockwise moment is negative. Or it is M2 minus M1 if you assume that clockwise moment is negative and anti-clockwise moment is positive. So please understand the difference. When we draw a bending moment diagram, then it is to be drawn based on whether the bending moment is sagging bending moment or hogging bending moment. When we say it is positive bending moment, negative bending moment, implicitly it means whether it is sagging or hogging. But then when we write the equation, then bending moment in same direction means whether it is anti-clockwise direction or clockwise direction needs to be added and subtracted. And same thing goes for your shear force diagram as well. Okay. Please explain it more easy from thinking. Okay, somebody asked again that I'm unable to understand degrees of freedom. Will you please explain it more easily? Okay, so let me give you another example. This is a very interesting example. Suppose you take a pendulum. Okay, this is a pendulum. This is okay. This is hinge. Okay. Now, how this pendulum will rotate? Pendulum. This will be the position of the pendulum. Suppose length of the pendulum is L. This length of the pendulum is L. Okay, and this is theta. Okay. Now, though this pendulum is, the movement is on a two-dimensional plane. Now, to characterize, say that degrees of freedom, as name suggests, it is the freedom of an object to move. How it is to be calculated, how it is determined. It is the number of independent information, quote unquote. I am intentionally using the word information because in this context, probably the number of independent coordinate is the more precise word, but let us think in this way: number of independent information we need to characterize the movement of this body. That is how we determine the degrees of freedom, right? Now, suppose the position of this position, this is x direction movement and this is y direction movement. Now, had it been any, had it not been a pendulum, had it been any object in two-dimensional plane moving like this, then I just mentioned the degrees of freedom is 3. One is 2 translation and 1 rotation. But look at the context of this example. Now, I want to characterize, I want to understand, I want to define the position of this pendulum at a given time instant. And in order to do so, what information do I need? I need the information only theta. Because if L is constant, then just if we know for a given position what is theta, I can calculate what is the position of this pendulum. So x and y both are a function of theta. So if we know theta, I can calculate what is x and what is y. So in this case, the degrees of freedom for this will be only 1 theta. That's why we use a general, in subsequent courses you will see we'll use a word called generalized coordinates, introduce the word generalized coordinates and all. So please again try to understand, is the independent, if we any information in addition to this will be are not independent. Any information in addition to that will not give us more info, will not be used to characterize the position of this object. Okay. That's why the word independent is very important. Now, I am telling you this again. The correct way or the precise way of looking at it, probably if we look from the solving an equation or solving a linear system of equation using matrix operation, and there we'll see that that why this independence come, what is the linear independence. So those are the things probably we'll see in linear algebra course or then matrix method of structural analysis course. But just to understand the degrees of freedom, to visualize the degrees of freedom, what is important to is to have this sense. Okay, so I think this is clear. Yes, as someone said, the degrees of freedom are the equations condition which facilitates us to express the location orientation of a structure in which it currently is formed or previous location orientation. Yes. Now, so let us move on. So we discussed what is the sign convention, the common confusion in sign convention. Then another confusion is I have seen the zero force member in truss. You see, when I say zero force member, it doesn't mean, for instance, suppose take an example of this. This is a truss, right? Okay, this is a truss. Let us not bother whether it is determinate or indeterminate. And this truss is subjected to some load like this here. Okay. Now I hope you can see the screen because there is a time lag. Yes. Great. So In this case, suppose it is A, B, C, and D. And if you look at member BD is a zero force member. Zero force member, why? The force in member BD is zero. So if we draw the free body diagram of joint D, so naturally this is F DB, and this is F DC, and this is F DA. So there is no force either external or internal to balance FDB. So FDB will be zero, right? That's why it is zero force member. Now in the same truss, again in the same truss, if we apply a load instead of load at B, if we apply a load at D, a downward load at D, downward force at P, okay, at D. Now you look at this diagram, look at this truss, and this is your support condition, of course. Now look at this truss. Then if you draw the free body diagram of joint D, this is FDC, and this is FDA, and this is P, and this is FDB. So in this case, FDB will not be zero, FDB is equal to P. So in this case, FDB is not a zero force member. So when we say something zero force member, it all depends on the loading condition. It is not that for a truss for a particular load it is zero force member, means the member of that truss is always a zero force member. It is not like that. When we speak a zero force member, it is always in the context of the given load. Okay. Okay. Now let us take another question. This is a very important assumption of Euler-Bernoulli beam. There are many assumptions, but the one of the important assumption, and I have seen that students make a common mistake. If we ask that what is the, there are two parts to it. One is to state the assumption correctly. This is one thing, and the second thing is to comprehend the assumption, understand the physicality of the assumption, and how this assumption makes our life easier in the context of this, in the context of derivation of beam theory. Okay, one of the important assumptions of Euler-Bernoulli beam theory is the plane section remain plane, and the normal to the neutral axis, the sections are normal to the neutral axis, then it remain normal to the neutral axis even after bending. That is the complete statement. Okay, it is not what I have seen many times is whenever I ask student what is the tell me the assumption, the important assumption of Euler-Bernoulli beam, then I get to know that plane section remain plane. Plane section remain plane is an incomplete statement. Plane section remain indeed plane, but then there is more to it. If the section normal to the neutral axis remain also normal to the neutral axis. What does it mean? It means essentially this. Suppose if you take a beam and okay, if you take a beam like this, and these are two sections, and suppose this is the neutral axis of the section, okay, and then after bending, this is the neutral axis. Okay, again, I draw the neutral axis solid line so you can understand. So before it is 90 degree, this is 90 degree, means normal to the neutral axis, and even after that these angles remain 90 degree. That's what this this assumption says. Now when we say this angle remains 90 degree, means you have to take a tangent to this neutral axis, and there's this angle between the tangent and the plane remain 90 degree. Now what is plane section remain plane? The physicality of the assumption is, if you look at the dotted line here, this is the undeformed configuration, and then if you see the red one, this is the deformed configuration. Okay, so you look at this line, this dotted line at this dotted line, this one, the initially plane one. Now this becomes this. So this is no longer a plane. This is not a plane. This is not a plane, right? So this is an actual deformation the beam may have. Okay. But then this assumption is, if your deformation is small, then this line can be idealized, can be represented through a straight line, So this is your straight line before bending. After bending, it may not remain a straight, it may not remain a plane, but if the deformation is small, then we can assume, we can idealize this as a plane, and this is our idealization. You recall, idealization is one of the important steps we do in any analysis, and idealization depends with every idealization is based on some assumptions, right? Here our assumption is the deformation is small. The assumption. So in many cases, the deformations are not so small that it can, in those cases, when plane section remain plane, the allability assumption cannot be applied. In those cases, we have to consider this kind of deformation, the actual deformation in a beam. We have the Timoshenko beam theory that will probably study in strength of material course or solid mechanics course in the subsequent semester. How this assumption makes our life easier? This is that if you assume that your section remain plane, then a section which is initially this, and this section now becomes, this section is now becomes this. So this is your nucleus. Nuclexes will go like this. Nuclexes will go like this. So this is initially, this is 90 degrees. So this will also be 90 degree. This will also be 90 degree. Now the physicality, how these assumptions make our life easier is, now if this plane is this initial plane, and after that this becomes, then of course there is a longitudinal strain in this direction, isn't it? Which is called bending strain. Now, due to this assumption, we can, due to this, the longitudinal strain across the depth of the beam can be taken as linear. This is the linear strain. Otherwise, the longitudinal strain cannot be. So this is, you will see when we next semester will be studying design of RC structure. Then in that case, you will see that these assumptions will make your all the derivations very straightforward. Okay, so this is the physicality of the assumption. Okay, so let me see the forum. See, internal external indeterminacy is your external indeterminacy is the indeterminacy because of, for instance, if we take a frame like this, okay, now make it okay, first make it ruler. So this is a determinant. Your number of equations, you have a two unknown here and one unknown here. You have 3 degrees of 3 equations. So it is determinate, statically determinate class. Now then, but then if we make the class like this, you make this is fixed and make this is hinge. Okay, so you have 3 reactions here and you have 2 reactions here. So total your reactions are 5, number of equations available 3, so your static indeterminacy is 2. This indeterminacy is due to the addition of more constraint in the form of supports. Okay, this is called external indeterminacy. Okay, now suppose in the same class, same frame, if this frame is stable, okay, this frame is stable, but in the same frame, if we add one more member like this, then what will happen? Even without this member, this is stable. Even without this member, the frame is stable. But then if we add one member, this means we are adding more unknown to the system. And what are those unknown? The member forces, the bending moment, shear force, axial force in this member. So we are adding more unknown to the system, and therefore we need to have sufficient number of equations, isn't it? So these additional unknown which cannot be determined through the equilibrium equation, this also makes your structure indeterminate. But this indeterminacy is called internal indeterminacy. Okay, because it is because of the addition of member additional member given in the system. The internal forces of the members need to be determined, and you need to have sufficient equations for that. Okay, this is indeterminacy, and if you recall that for this, you try to find out if you add a member like this, your number of internal indeterminacies will be 3. So total in this case, indeterminacies will be external will be 2, and internal will be 3. So total 5 indeterminacy. Okay. Okay, probably I'm okay. There is a question like why maximum bending moment does not give maximum deflection. Intuitively, how can we relate it? Okay, see, maximum bending moment. If I give you an example, you take a beam, you take a cantilever beam, and apply a load P here. Then we know that the bending moment diagram will be this, isn't it? So here your bending moment is L. So here is bending moment is PL. Here is bending moment is 0. But when the beam deflect like this, isn't it? So so deflection, the maximum bending moment and maximum deflection. If you have to relate bending moment with deflection, then you have to relate through the equation of elastic line. If you recall the equation of elastic line, d2y dx2 is equal to minus m by ei, right? mx by ei. So bending moment and displacement you have to relate through this. You have to relate through this. You cannot just say that your bending moment is maximum, that's why the deflection should be maximum. No, this condition gives you the where the bending moment will be, your deflection will be maximum or deflection will be minimum. Okay. Now you look at that for maximum y, what should be this term? You have to determine. Okay. Different types of software used in civil engineering domain. Okay, so NPTEL can organize a course where we can learn different types of software used in civil engineering domain. That will be helpful for us, like StatPro, ETABS, etc., like design software. I doubt whether software can be taught because of some copyright issues and all. But yes, programming can be taught. You have a matrix method of structural analysis where matrix method of structural analysis where you see all the analysis in structural analysis, the purpose of structural analysis. If you look at the entire syllabus, we studied so many things, like we studied moment distribution method, slope deflection method, the method of consistent deformation, we studied three moments theorem, so many things we studied, right? But if you go to industry today, it's not that those methods are used for analyzing real life structures. Okay, those methods are, but still we use them. They were developed many years back, but still we read them, study them, because they give us the they help us to develop the sense of structural analysis. Okay, so suppose if I apply a moment at a joint, then that moment will be distributed, but that moment will be shared by all the members connected to the joint. But then we should be able to assess or visualize or have a sense that how this moment get distributed in different members. So the concept of moment distribution will help you to do so. So the purpose has been to set the platform where you can learn more sophisticated, more advanced technique for structural analysis, which is, if you recall, you were probably at the 10th or 11th week of the course, in the last week of the course, and probably last two lectures in the closure, we discussed that all this information that you have learned, or all these things that you have learned in this course, then what is beyond that, how you take this course to further take this course or take the learning from this course to study more sophisticated, more rigorous analysis technique. So there probably you'll be having some introduction to not software but some kind of programming, how these the at the end of the day your analysis method should be very computer friendly. Please note that when you go to industry you won't be solving a cantilever beam, or you won't be solving a simple truss problem. You will be analyzing a stadium, you'll be analyzing a multi-story building, you'll be where there'll be thousands of members, thousands of joints, or there are sometimes many thousands of joints. So those cannot be solved manually using all the methods that we have learned so far in this course. For that, we need some method which is more rigorous, scalable, and can be translated into computer code. Okay, so their matrix method of structural analysis or direct stiffness method is one such technique, and in that course you'll be having some exposure to some software, some programming. Okay. And okay, this reminds me one very important thing. I'll come to the questions that you were asking in the chat box. This reminds me one very important thing. See, if you look at all the lectures, there are few places, particularly where I tried to solve some numerical example. Not all the places, very few places, 2 or 3 places. There will be some there's not calculation mistake, but the mistake in this order, like I am telling a positive moment, but while writing I'm putting a negative sign, or I am telling a negative moment, but while writing I forgot to give the negative sign. Okay, or I am telling static indeterminacy, but while writing I probably wrote kinematic indeterminacy. So mistake of that sort. So there are few places we do have such kind of that may create some confusion, but then when you watch the videos and they do the exercise, please put the entire thing in a proper context and try to comprehend this. Okay, so this is very important. Now, then okay, some of the questions that you were asking here that requires a long answer and long explanation. What I do, I may write them and post it on the forum. Because of the time constraint, I may not be able to go through all the questions that you are asking. I'm just putting only those questions which can be answered in just 1 or 2 minutes, and then we can respond to many questions. But I really take a note of some of the questions that you are asking, and in a couple of days time I'll post it on the forum. Okay, which may need some kind of derivations, which may need some kind of solving. No, there is no. Yes, there are design courses on NPTEL, like design of RC structure, design of steel structure. Yes, like one could, like how to idealize impact load and blast load, and then question on Beatty's theorem and relation with energy, strain energy principle. So those questions, what I'll do is I'll just put it on the forum, because I need to write. I need to discuss all the things in detail. Kinematic indeterminacy in a frame where axial deformation is assumed to be 0. Yes, I mean, for instance, I take a simple case. You have suppose let us make it fixed. Okay. So what is the kinematic indeterminacy in a frame? You have a 3 degrees of freedom here and 3 degrees of freedom here. What are those 3 degrees of freedom? This, and this, and then you have this, and this, right? So you have 6 the kinematic indeterminacy. Now then, if I put the constraint that there will be no axial deformation. Okay, if there is no axial deformation, then what will happen? See, if there is no axial deformation, then there will be no, this won't be there, right? This won't be there. There is no axial deformation, this won't be there. if there is no actual deformation, then what will happen is, if this is A, this has to be A. If this deformation is A, this deformation has to be A, right? Because the horizontal displacement at this joint and horizontal displacement at this joint cannot be different. Otherwise, there will be actual deformation. So this is one kinematic indeterminacy. In terms of that, you have a rotation here, rotation here. So you have three kinematic indeterminacy. Okay. Method you are taking a mechanical would be applicable for. Finite element method is a very general thing. It has nothing to do with whether it is a civil engineering problem, mechanical engineering problem. Even today, if you take any branches in engineering and science, and I just go on to tell you that any branches of non-engineering and non-science as well, finite element method, there is a use of finite element method, and the basic concept of finite element method remains same. But yes, depending on which discipline you are studying, your applications domain may be different, but the finite element method will be always same. Okay, and for some of the questions, you please refer to the courses and the what is called and the assignments. Okay, another question that have been that I received from few students, that the concept of stiffness, that you see, when we talk about stiffness, this thing we know that if you ever take a spring, and then if we apply a force P, and then if the spring constant is K, then the spring constant Kp and the deformation related to this P is equal to K into X, right? And K is equal to P by X. So K is the stiffness, which is the force required for unit deformation, unit displacement in this case. So it's a very straightforward, we know this. But in a three-dimensional object where the forces are from different directions, there are different components of the deformation, then you cannot really say the stiffness of an object is like this. Stiffness of a spring, you can say probably, if the deformation is only one particular direction, but where you have deformation, you are dealing with a three-dimensional space or even multi-dimensional space, then you cannot say the stiffness of an object. This statement is not correct. So whenever you talk about stiffness, there is two things important, that which load and which deformation. That is important, because if you change the combination of load and displacement, the same object may have different stiffness. So for which load you are talking about and which displacement you are talking about. Just to give you, just for an example, if you take say a propped cantilever beam, and then if this is A and this is B, and if we give some moment, say this moment is MAB, and this will generate a fixed end moment like this, which will be MBA, and then this beam will rotate something like this, and this is theta A. This is theta A. Now theta A and then theta A and MAB are related like this. MAB is equal to your 4EL, 4EI by L into theta A. And MBA is related is 2EI by L into theta A. Now when we were talking that moment AB, this combination, moment at A and the rotation at A, then your stiffness will be this. And then if you are talking about this moment at B and the rotation at theta, then your displacement will be your stiffness will be this. So it depends on which combination of force, wind, and displacement you are talking about. Okay, so so this is last, as I have to finish by 11:50. Last thing, this another confusion I have seen related to the internal hinges. Internal hinges is For instance, if there was a question in assignment 1, the problem 2, I'm not going to solve this example here because it is the solution is already uploaded. But the internal hinges, you see, if you have a beam like this, it is a propped cantilever beam, okay, and it is subjected to different kinds of load, then we know that this is an indeterminate structure. The static indeterminacy is 1 because 3 reactions here and 1 reaction here, 3 equations, and static indeterminacy 1. So we need one more equation to determine this additional, the one unknown. Now, if we put an hinge here, if we put an hinge here, internal here, hinge means it cannot take any moment, right? So see, moment at this point, it allows rotation to happen. So moment at this point will be 0. So if this is AB and this is ABC, so we can say, because this is internal hinge, we say MC is equal to 0. So this gives you an additional equation, okay? Now, in some example, you have to break the problem, draw the free body diagram and solve it. You may not have to break the problem, just apply the equation MC is equal to 0. It depends on the problem you are solving. You have this hinge, it will give you an additional equation. That equation can be used to determine the additional unknown. So almost done, because I have just received a message that I have few minutes left. So few questions. Indeterminacy of a truss is, we know that MJ M plus R minus 2J. This is the indeterminacy of a truss. In truss, what happens? All the members are two force members. So unknowns are just this M stands for number of member, because every member has one unknown, is an axial force. So M is the total unknown, the internal force, unknown of the internal force. R is the total unknown of the external reaction. And 2J is the number of joints that J is the number of joints, and 2J is the number of equations that is available. Okay, so therefore the total unknown will be number of reactions plus number of internal forces, and then minus the equations we have. That gives you the total indeterminacy of a truss. Okay, static indeterminacy of a truss. Okay. When any structure is subjected to external load, then reaction force of respect to it, or in case of equilibrium, click only the reaction force. When any structure is subjected to external load, then reaction force or member force both respond to that. But in case of equilibrium and stability, what is your question? I didn't understand, Ranjit. And okay, let me go through, browse through the other questions. Okay, so as I said, the time is short, so I have to stop it here now. It's nice to have this interaction. Unfortunately, there are few questions still left, which I picked up from the forum and from my personal email, and there are few others that you have asked in the chat box, but I will definitely respond to each of you in a couple of days' time. Or I'll put all the answer to the forum. Okay. And so I'll stop here today, and I hope that there are another course on structural analysis, that is matrix method of structural analysis, which also being offered in the autumn semester. So that course is a bridge between structural analysis and finite element method. So you may like to have that course as well. With this, thank you very much. So